Ah. Okay. Yeah. I think, okay. So how about the other people here? Huh? First two completed. And 2.5, how about 2.5? No. Okay, because that's what I wanted to. I think it's a good idea to, see what's going on, Yeah. So, but the problem number 2, you think it's controllable and observable or controllable? Did you check that out? I think you need to check that out. There are zeros in one of those columns. Try to check it out. Okay. Okay. Yeah, you need to AC and BC, you're calculating using A and B. That is correct. But remember, you're doing that, but in real practice, you only see AZK, BZK. You don't see A and B. Only for the purpose of control design and for testing or verification, we are doing you're computing AZK, BZK. Remember that. So when I'm trying to control a process with the network control system, for me it appears like AZK, BZK, with AZK and BZK unknown. Yeah. Right. So it does work. Right. And the reason that those are is just to show how we can transform a system with a network in the loop into a linear network control system. That's basically it. And even if you transform it, even though you have A and B known precisely, what we are claiming is the AZK, BZK is still unknown. Remember that. That's another reason. Why? Because the delays and packet losses are not precisely known. You see, you understand, right? Even if you know A and B precisely, and when you bring that network inside that feedback loop, you would have a AZK, BZK, whose values are not known because the network delays are unknown. It's random. Yeah, that is correct. So when A and B are unknown, definitely everything is unknown. Whereas if you know A and B, even then, AZK, BZK, the dynamics are unknown. And the reason is unknown is because of the network, which is a random variable. Yeah, you only know the distribution you might have seen, but not the precise values. And that changes the AZK and BZK because you won't know. Okay? All right, any other questions, guys? I know some of you came a few minutes here. So I was asking if you guys have completed your assignment 1. Because now today afternoon, we're going to move on with assignment 2. That's why I was asking. How many of you how far are you guys? You have done 2. How about 2.5? Okay, 2.5 is what they said they had some issue. I was asking them to check the controllability in general. But if it is controllable, we are able to do it, then there is some other issue. Yeah. The dimensions, like you said, yeah. Check. Yeah, dimensions, so you have to check. Okay. I think, yeah, please do check that. I think those are important, I think, as part of this. See, this is one reason why we can do everything within one day, right? Because we got stuff going on. If it's a semester long, you have a little more time. Yeah. But you can figure it out, even though, you saw it should work. There's no difference. Yeah. sometime. All right, guys. How about you guys at the back? Two problems I was asking, right? 2.5. Anybody do 2.5? At least they are far ahead. They say that 2.5, other than 2.5, everything else is working. How about you guys? Any experience? You have not done that. But how about 2.2 or 2.3? 2.2? Yeah. All right. So I think try to do this. It would make it easier. So today, I keep moving. So that's why I was asking you. So now we are going to go into nonlinear network control system. So far we did linear. Now we would take a system that is nonlinear, and the question was, it's the same process. How do you come up with a FZK and GZK? It's very similar with the packet losses and delays, right? It's the same integral, so there's no difference in there. But I'm just saying, and then we want to use, since it's nonlinear, we have to use neural network. Okay? So this is lectures 7 and 8, so hopefully we can do 7 today. All right? So if you look at this system, here you see there is the continuous time plant, which is nonlinear. You have a state quantizer. Okay? So let's assume that you don't have state quantizer for now. And you have a delay in packet losses. Let's assume that. And you have a discrete controller. And normally you have another quantizer. And then that goes through the network. And then you get the actuator receives the quantized control input. This is typically what it is. Okay? So initially we can remove these quantizers and just use only delays and packet losses, because we know how to handle that, the quantizer. So very similar to our linear, we still have the same block diagram here. So when you send a sensor input, it takes so many seconds delay through the network, and from there, from the controller receives that, and from there it takes another a few seconds. We call this whole time called round trip delay. It's a round trip delay, okay? So this is what they talk about in networks. It's called RTT. That is basically this whole thing. It's a round trip. It's a closed loop, kind of closed loop delay. So that delay, and ultimately you see that it reaches the actuator. So there is a little bit of a delay there, and that delay varies because of randomness in the network. You see? So we assume that it has a bound, but ultimately sometimes you may not. So the network can hang up and things may not be flowing through the network. Right? Remember that sometimes you have a congestion and you have to really turn it on and turn it off, basically. Okay? So you can see that top line sensor packet sent, middle line controller receiving the sensor packet, computes the control input and then transmits it, and then bottom line is the actuator receives control action. Okay? So there are some assumptions you need. One is the sensor is time driven. So that means that the sensor is basically measuring the state vector with respect to time. Communication network is a wide area network, so that the network-induced delays are independent and unknown, whereas the probability distribution functions are considered known. So what it means independent is, you see that the same network you are using for sensor to controller and controller to the actuator. So for sake of analysis, we assume that these values have nothing to do with these values. So it has enough bandwidth that these two sites are independent. That's the assumption there. Okay? And you only know probability distribution. This is what I was telling you. You don't know precisely the delays and packet losses. That's why the dynamics becomes unknown. Even though the original system, like you guys were looking at linear system, even if A and B matrices are known precisely, sampling interval, then you are running open loop. And as I said, so in with event triggering, many times we extend sampling. But initially, when you don't know the system dynamics, mathematically what we have shown, although I'm not going to cover this, you have to sample more often. Why? Why? You understand what my question is? Okay. So one thing we said, the sampling interval, like the delays, has to be less than a sampling interval or something close enough. But we can still handle when the delays are over a sampling interval. That means when it goes more than a sampling interval, the system is running open loop. Make sense? Everybody understands that? Okay. So my question now is, let's say there is event triggered paradigm, okay, where we stretch the sampling interval, okay. So the question was, if the delays are more than a sampling interval, okay, assume that, and you don't know the dynamics of the system, you don't know the dynamics of the system, why extending the sampling interval would fail? It's even with adaptive control this happens, or learning based control this happens. Why does it fail? Right? But that can happen even with known dynamics too, right? Even if A and B are known, let's say you stretch the sampling interval. Let's assume that, okay? Don't worry about the losses, whatever. Even if you know the A and B, let's say you stretch the time in sampling, that means the system is running open loop, right? And it can become unstable because it's not closed. But my question is, if A and B is unknown, for example, why is it even more important to sample more often? Do you understand that question? Okay, so you see what I'm saying? So let's say that if you know the dynamics A and B, you're stretching the sampling interval, so that means you're running the system open, okay, right? So it so happens that you don't get the feedback on time. Sometimes it could become unstable because there's a margin of stability, and so forth. But this is even more severe when the dynamics are unknown, rather than the dynamics are known. Why? And what happens when the dynamics are unknown? When we have seen all these controllers. You guys have ran the Q-learning controller. Why is that important that you got to make sure that there is enough samples? Why? I don't know, most of you never asked this question. This is very important. This is part of the learning stuff. One is to run the code and show some plots, right? The other one is what is happening here. So why is that when the system dynamics are unknown, it's even more important to do the sampling? But she has a hint there, and we have to use her hint. Now, let me help you. So let's say you're trying to learn, okay? What do? Let's say the controller has to learn something. So what does the controller need? Data. That's right. So you mean AZK and BZK are present, and the dynamics are unknown. The first few seconds, the controller is trying to learn and understand the dynamics. That's what is happening in all these controllers. Right. That's why, since the error is more, it's trying to understand and tries to find the error. So the first few samples are extremely important. Now, so when in the point of learning, when you're stretching that time, that means you're not getting enough information from the system. So the controller is unable to learn and it can cause the system quickly unstable. So remember that. So as you're learning, it's like practice. You've got to have some information coming through. Then only you know whether what you're doing is correct or not. So in the steady state mode, that's okay. So if you remember when I did the event trigger control papers, what happened is when we were doing that using neural networks, always the sampling interval will be equal to the event triggered sampling interval will be equal to the regular sampling interval initially. This is just adaptive. And after that, once the dynamics are learned, it starts stretching. The same. So this is very critical. Yeah, you can see that very nicely in that the way the mathematics works.
If it is unknown, then hidden dynamics, faster dynamics can be.
It has to be stable. There's no doubt. And the same thing, right? You know, in order to stabilize it, let's say even if it's stable, in order to stabilize it, and it's unknown, so you got to get that information so that your controller is trying to tune those gains, whatever.
Initially, the sampling will be dense.
Right, exactly. After that, you can start stretching. Yeah. So if you look at many of my papers, that's how it looks like. Yeah. So maybe if I cover, I'll show you if I have anything on that slide. But yeah. But that's what it is. So the reason why it happens is because the controller is naturally trying to learn the dynamics initially, and that's why you have more samples. You can't go any smaller than a sampling interval. So therefore, that time, that event triggered sampling is equal to the regular periodic sampling. And once it learns, then you will see that it stretches the event triggered sampling. So keep that in mind. Okay, so that learning part in there. So that's why I think it's also equally important that you really don't want to have the delays, some of the delays even more, primarily because then you're running the system open loop. And the controller is unable to what is it doing? It's basically probing and through the data and trying to understand what the dynamics are so that it tries to learn from it. So now it's not there if you stretch the time. You see? And this happens even for human. Right? If you imagine you have to go to a lab, you have to do some tests. Let's say that lab is closed whenever you're coming in, what will happen? What will happen? Yeah, you're not getting access to it, and so you try it for 10 times, 20 times. After that, you get fed up and say, well, this lab is closed always, and I hell with it. So same thing. Yeah. So you have to have some data that it needs. So that's important. But either way, this is a very critical assumption. So the total delay has to be bounded, but it has to be reasonable, and that value depends on the practical system. It's not the same. So some systems are slow. Maybe you can handle longer, but some systems are very fast. Then you may have to have a faster sampling interval. Okay? All right. So this part we talked a bit about it, like linear network control systems, known dynamics. That's what people have done in 1988, and you can see that. Then optimal control for linear NCS with known system dynamics was also done in 2002 and all that. But it's all known dynamics basically. And stable control of nonlinear network control systems with known system dynamics was also done in 2001 and 2003. But what we are dealing with is, well, can we do optimal control for nonlinear network control systems with unknown dynamics? I think that's basically what we are all interested. And can we do that some way like using an adaptation, right? Learning an adaptation. And that's basically what we are trying to do. And it's a nonlinear. In the linear case, we use Q-learning. In the nonlinear case, we already learned neural network stuff we are going to apply here. So basically, we are going to use neural networks. And since we are using neural networks and dynamic programming, remember that L10 equation? Basically, we call that as neurodynamic programming. And so it has very similar relationship with reinforcement learning because you get the Bellman equation and all that. And use that temporal difference error, therefore that's basically how we claim it's a reinforcement learning. Okay? So wireless imperfections can cause significant challenges which are considered here. So you see that originally we start with the same thing that we did, a nonlinear system in continuous time. Just like we did in the linear system case, you integrate it, and the book has a little more details. So if you integrate it, you do like what you did, kt to tau d minus dt, very similar like what you just said. And you end up in getting, there are two different ways you can write this system. One is you can have a z of k. The z of k, you can write it control input, or you can take the output and you can mention output and then previous control inputs. So you can have your dynamics can be expressed either using measured state value like here or using measured output. In either way, you end up in getting a form of equation like this, which is z of k plus 1 is h times z of k plus l times this, times u, y is equal to c naught. So, just like a linear system, this becomes discrete time, h and l are become unknown. Okay? So, h and l becomes unknown. The uncertainty is coming in because of delays and packet losses. Very similar. Okay? So the same thing you can do. Let's say if C is convertible or invertible in this case, then you can write this dynamics. Okay, and this, you can write it in the form of what we call input-output data. Somebody was asking me this. So you can write it as input-output rather than state. So if you do that, you can actually come up with another equation like this in terms of y of k plus 1. Then you can write that y of k plus 1 is f and g, and this f and g basically are functions of the outputs. See the yk naught is basically defined as the current value of the output and the previous values of the input. So you can actually transform that system either using the outputs or using the states. You see what I'm saying? So only you need to remember is what is your augmented vector that you're going to do. Does it have the output or does it have the state vector? Any questions here? So the design is the same. No matter whether you do the input-output form, equation 3, or you do use equation 2, the design is same. So I'm not going to give you the difference, you know what I mean? So it's very typical that y is measured. But there are a lot of places you look at when what happens when x is measured. Okay, what's your question? Here we don't use the observer because you are converting the system into input-output form. So what the good thing with this is you don't need the observer, but you still need an identifier because the f and g is unknown. So now you are building the f and g using the outputs. Exactly. So we don't need an observer, but you need an identifier. Got it? So you see the difference, right? An observer sometimes can be identifier, sometimes is not. And that's the difference. Yeah. Okay, any other questions? I see some new faces at the back. So you are new faces? Yeah. You see? So what's going on? You didn't come all these few classes? Okay. But I think there's a sign sheet, I think, right? Yeah. Okay, so I know the people who are on the left side, and except one or two people, they have been periodically coming. And this side is mainly those people who come and go, like a random. Yeah. All right. Okay, so is that clear now, right? There are two systems, but I'm not going to go through each of them. It's basically the approach is the same. Okay? So in one case, you are using the state, x of k. In the other case, you are using the measured output, but the ideas are all the same. Got it? Okay. So now, since it's nonlinear and unknown, we use the same ideas of dynamic programming and the reinforcement learning. So what we are going to do is we're going to define a value function or a cost function. Let's assume you're doing with respect to the state. So it's the expected value of this, okay? And you see that this is quantized input here, okay? And then on the other system, you replace the Zi with the output vector. Remember that we defined. So it's the same thing, okay? And this has got the infinite horizon. And here Qy is C naught inverse Qz C naught, Ry is Rz. So same thing, you know. So now, let's go back and look at the traditional optimal control, just to recap. So if I have a nonlinear system, and if I don't have the network delays and packet losses, let's say FD and ZD are nonlinear. Okay? So the way you come up with the optimal control is you first form the Bellman equation, right? The recursive equation. And it has this is a finite horizon, n minus 1. So there is a terminal constraint. There's a second equation. Okay? And then what do you do? This is n minus 1. This is up to n minus 1. K going from 0 to 1 up to n minus 1. And this is n. K equal to n here. Okay? So then what you do is you write this in the form of Bellman equation, a recursive equation. So remember we said k to n minus n is equal to k to k plus 1 and k plus 1 to n. Recursive equation. Okay? Then to find the optimality, what do? You basically move that left-hand side to the right-hand side and take the partial with respect to UDK, because we are trying to find the optimal control input. So you take that partial with respect to UDK. So here is the UDK. So if you do that, then you get this expression. And then from there you are getting the optimal control input. Okay? So the optimal control input is R inverse. It requires the G matrix or G vector, whatever. And then it takes the partial V star over future value of the state. So this derivative, we don't have it. And if G is unknown, we also don't have it. So when we don't have the dynamics, we have to use two neural networks. Remember that. Or you have to use an identifier. Okay? So that's number one. We already have seen how to tune this. Because remember we saw that last class, we used to tune the critique. We use what error to tune the critique? So we need two error terms. One is to tune the critique. The other one is to tune what? The actor. So the critique is tuned by using Bellman error. Exactly. Don't forget that. And if there is a terminal constraint there, you also get the terminal constraint error and you sum them up and you use that to tune that. Remember that? So, but then to tune the actor, what error do we use? To tune the actor, we call it as a control input error. Control input error. So that basically the same thing that we're going to apply here also. Okay? So we are going to do the cost function and then we're going to define the control input and we're going to do the same. So that's why I think we have that reinforcement learning I gave you without all this network control, the same idea. The only difference is we are dealing this with expected value. There we don't have to put the expected. That's the difference. Okay? So in this case, that's what we do. And you plug this optimal control input back into this, you get the HJB equation. So this equation is the HJB equation. And the HJB equation, like we talked about it, it's a function of the dynamic and it's unknown, there's no closed form solution. So you have to either solve it offline, numerically. In this case, what we are doing is we are trying to solve it in real time. Okay, so now we try to do that with network in there. So now, you see, I don't have quantization. So I have a network. So I have these delays and packet losses. So I'm taking this continuous dynamics. I follow the same process here, and then I get a discrete dynamics. Okay. So you see that f of zk, g of zk. So f and z are unknown, right? So now we will use an identifier, first step. So the identifier, the purpose of the identifier is to estimate f and g. Okay? So the same approach that we used, you write the dynamics, you see that one big neural network. WF and WG are two parts. One for approximate f, the other one to approximate g. And we are combining into one neural network, okay? And by doing that, we also get this 1 and UK minus 1, that becomes capital UK minus 1 here. So we make that as a vector, and we are basically combining these two matrices into one matrix, and then we are tuning it just, okay? And so then what we do is, we are trying to find the actual weights, which is approximated by the neural network. And so this is the identification error, z minus z hat, z is measured, z hat. And so now you're using the history. Now why do we need the history? I already told you. Why are we using the history? Because if you look at that error, the 6.16, it uses the history rather than individual values at every instant of time. Why? Why do you need to construct a history so that we get the same error equation in terms of the history? You see that zk minus 1, zk plus 1 minus f. So it's like an history. So 6.16. Why do we need the history equation? I said that. I did explain to you why you need that. Huh? To persistently excite him. See? I'm happy you are reading the material. That's right. And why do we need persistence of excitation? Why do we care? To identify, right? So that means, remember I said you have a black box, you are trying to feed some inputs, and you're trying to understand which inputs are going to excite what is in there. When I say excite, it's going to, if you have a resistor, inductor, and a capacitor, it's going to create such input so that you know, as when you measure the output, you know, this behaves like a capacitor inside. This looks like an inductor inside that. That's what it's doing. So persistency of excitation condition is very important. And at one value, it doesn't satisfy. You have to use the history, and it becomes a matrix. And we show that that matrix is invertible. If it's invertible with those inputs that you are feeding, you know, the signals, then we claim that it is persistently excited. Unless it happens, the identifier will not be able to capture what is F and what is G. Remember that. Okay? So the persistency of excitation is a condition that's usually needed for identification, and that's basically in the adaptive control. Now, in the 2010 work, if you remember, I gave the paper. So there is a guy, Girish Chaudhary, he came up with the data, using data, they call that as a concurrent learning. So instead of doing this, because the condition is so hard, they use the data, which is very similar to what we are doing, but we never call concurrent learning. But that data he used, and he was building a matrix as you controlling the system, and then he's creating that PE condition. It's a really nice paper. Yeah. So with data, you could create that. Okay? And that's what we are doing here. So with data, we are able to create it, and then we use this equation rather than that, basically, for our analysis. Okay? for our analysis, that equation is being used. So then the steps are very similar. So basically you take that equation and you do the analysis. So all these steps are pretty much in the intermediate step Z and this one. Here is the update law. Remember, this update law is the least squares. Least squares update law. It takes that error equation and takes the gradient and you end up in getting that. And when you plug this equation, you end up in a exponentially stable. This alpha I is a positive quantity. So this system is exponentially stable. That means that the identification error converges. Okay, this is the ideal case. And this is a very good thing about that, how we came up with that update law. And you see that the PE condition is needed here in order to show that this matrix is invertible. That's why we need the PE condition. So if you don't use that history, that matrix will not be invertible. Any questions? So this part is very similar to what we have shown before. So nothing new about it. Any questions, guys? Okay. So now you see that because this is expected stuff, we prove that it is bounded in the mean, boundedness in the mean. Otherwise, we just show boundedness. So here we show that this is expected of this boundedness, so therefore we call that as a boundedness in the mean for the neural network identifier. So here you show the learning rate has to be selected between 0, greater than 0, and some value which is upper bounded. And then the weight estimation error are all bounded in the mean with the fixed final time 0, comma, NTS. NTS is the final time. Okay? Then you try to approximate the stochastic value function. So now we got the identification. The identifier would give you f hat and g hat, right? So now we are doing the value function. So value function also you use a neural network. You see that neural network here? And you see that there is n minus k. That's the time varying basis function. And I already explained to you, since this is a finite time, we are talking about compact sets, you are still okay to approximate. Okay, because the time is finite. Alright? And here is the actual value of the v hat. The value function v hat is the output of the neural network. W hat v k, and then here is the basis function. So the main challenge is this basis function. So how do you come up with a basis function in order for the controller to converge? So there's a lot of time we spent on that. So we did include also a saturation when we did the simulation. And what is the purpose of the saturation? To make sure that the values are bounded. Because for neural network approximation, the activation functions have to be bounded. Okay? So we had that issue of the time. And we're doing a polynomial because a single layer network, it has to form a basis. So we have to do a saturation in there. Okay? So then you get the Bellman equation here. Okay, that's the Bellman error. You can see that, that's the Bellman error. Once you get the Bellman error, then we basically find the update law for the Bellman equation. So you see that how it looks complicated now? In fact, the procedure is identical to what we did last few classes for nonlinear systems. But here, because of the expected value, it becomes really complicated. So you have two errors. One is the HJB error, and the other error is the terminal constraint error. So the terminal constraint error is this here. And the HJB error is here. So you have two errors, and we have to come up with an update law using those two errors so that you are adjusting those weights of the neural network. Okay? So here is the update law. Now look at this update law. This update law uses the previous value plus alpha v times this term. This is the average effect, right? This is 1 plus z. So this is the basis this value is always less than 1. Now, why is this always less than 1? Why is it always less than 1? Now, look at that equation. So let's say I have like so if I have an equation like this, a over a square plus 1 is always less than 1. Make sense? Everybody agrees or no? Is it true or not? So here, instead of a, this is a psi of this divided by psi transpose psi, which is plus 1. So that's the same thing. So this term is always less than 1. Then you are multiplying by the the terminal constraint error. Here you are multiplying by the HJB error. But you see that this is more like an averaging. So there are some people in nonlinear control, which is true. These type of update laws, if you take a nonlinear control, they slow down the learning process. But we are using it because if you don't use it, it's very difficult to show stability. So by doing this type of thing, in adaptive control, the nonlinear guys, Christie and others, they have shown that it takes basically a lot longer. Sometimes it may even become unstable. In this case, you have to use that kind of a update law. So this is the update law we use for tuning the critique weights. This is the actor. This is the actor design. Okay. So you are now designing the actor. So you use the, remember we said there are two ways you compute the optimal control and then you subtract one from the other, and we call that as a control input error. Okay, you get the control input error and then you come up with an update law for the actor. So you have an update law for the critique, you have an update law for the actor. So we are using 2 neural networks plus the third neural network for the third neural network is used for what? For identifier. We are using 3 neural networks here. So here is the flow chart. Okay. So the flow chart basically starts with what we just did. You initialize the value function and the control input has to be initial admissible control. Remember that? We talked about it. Then you first update the identifier weights. And then you update the critique weights and value function. Then you update the actor weights and control policy. You check whether the time is equal to final time. If it's not, then you update the time and you go back. Otherwise, you reach the final time and you stop. So this is how the simulation code is written. MATLAB. Any questions here? So the adaptive critique design is the same, whether you are using a network or not a network. The reason we use expected value here is primarily because the system becomes stochastic. And f and g, just like we saw in the linear case, f and g becomes a function of random delays and packages. See? Okay, any questions, guys? Yeah. You may have to raise your voice because of the fan. That is correct. You take the same measured states. Like the vector, augmented vector, remember? That's all you're doing. That's right. You use those augmented vectors. Okay? And that's all the things you are measuring, right? Only thing is you are combining. The reason I said augmented because you are adding those history. That's right. Any other questions? And it's the same whether it's a stochastic or a deterministic case. It's the same idea. The only thing in stochastic is you bring that expected value. Since his expected value, you see that under E, you put that delay and packet loss. Because it's basically you're taking the expected value because of those two quantities which are random. And that's the notation normally we use. Okay? Any other questions, guys? Any other questions? So the design shouldn't be confused, right? It's the same. Even without the randomness, right? It's the same design. So we are applying now the same design now in this. And remember I told you the control input error and the Bellman error was a challenge for us because how do you tune those weights? And you can use the same Bellman error for both and you try using it, it doesn't work. So that was a challenge. Okay? Alright, so here is a fancy controller block diagram. Alright, all different colors and even a little bit of shading in there. So you can see there are two cases here. One is you see that there is an identifier. Okay, so there is an identifier and then you see that here is the identifier history stuff that we talked about and it generates F hat, it generates G hat. And then it's using that G hat into the actor network. You can do any number of ways. And then you have the terminal constraint error, you have the Bellman error. These are used to update the critique neural network weights. Okay, and here we are using that G hat information to compute the U hat. And you're using the U hat. And you can see that this is a neural network, two-layer neural network. With first layer, neural network weights are selected at random and basically frozen. So for a basis function, it's very difficult to select. So somebody basically he does pattern recognition. He came up with the idea that you pick the input to hidden layer weights and you select it at random and you freeze it and only you tune the output layer weights. Then that particular way of doing it becomes still one layer of neural network and input to hidden layer weights form a basis. So we use that idea here and we are only tuning one layer of weights. Okay? So this is the block diagram for the controller and you can do that for the different system, and this is a different, similar idea, but a different system here. So it's a very similar idea, but the inputs, in one case you are using state vector, in the other case you are using the output vector. Okay, so here is the overall stochastic optimality theorem, convergence of the stochastic optimal control input. And you can see that there is a bounds on these learning rates for the critique, learning rates for the actor, all that stuff. It has to satisfy those conditions. Then we claim that all the closed loop signals are bounded. And the bounds depend on the final time instant, initial state bound, identification error bound, and the these are very critical and they're all bounded in the mean. They're all bounded in the mean. Okay? So this is kind of a theorem that pulls in all the stability. So here is a table. Okay, it's like a flow chart. I'll skip this. So let's take an example. So let's say you guys are familiar with this tooling robot now, right? So here is a tooling robot in continuous time dynamics where f of x is given by that. So dy dt of x1 dot equal to x3, do dt of x2 dot equal to x4. So rate of change of position is angular position is velocity for the toolings. That's what that is. And then the do dt of the x2 dot and x4 dot basically becomes that dynamics there. So this is f of x and this is g of x. Okay? So this is f of x and this is g of x. Alright? So here we are selecting the network parameters Sampling time 10 milliseconds, upper bound on the network induced delay is 20 milliseconds. So here is greater than the sampling interval. You see? Got it? Okay. So network induced delays, the sensor to controller here. So sensor to controller delay is about 8 milliseconds and the other delay is about 15 milliseconds. And network induced packet losses follow the Bernoulli distribution with gamma bar equal to 0.3. So you look at the Bernoulli distribution and MATLAB has a little command. You provide the gamma bar value and it generates that. And actually I have a plot, I think. So here is the delays and packet losses. So you see that the packets are getting dropped and you see 1 and 0, 1 and 0. 0 denotes packet is lost. You see? Okay? And that's random. So you see that it's not really periodic. So you see a drop here, you see a drop, next you see a drop here. So it's not periodic. You understand that? That's a random. I want to make sure you understand. So here is the sensor to controller delay with respect to time, and here is the controller to the actuator delay. That's also with respect to time. Okay. So we have that, and we put the total time. In this case, is about 2000. Final time is 2000, and we repeated for the sake of ergodic behavior. 1000 iterations. So one of the questions I asked you was for you to check what is ergodic behavior. Anybody check that? So what was the meaning? You need to speak louder. Because of the fan, they can't hear you. Right. So time average is typical with the regular deterministic. Here we are doing ensemble, that is taking many, and then you are averaging it out. That's why we do that. Ergodic behavior, so it will make sure it's safe. Okay? I think any questions there? Do you guys understand what she said? Okay. And you are nice to her. Is that why you are nodding? You really understand? All right. Okay, any other questions here? Any other questions? So this is what is happening, right? Then the other things we need to determine. One is you see that the augmented vector. Here I am selecting x of k just for sake of argument. I only pick two former values of u. Okay, so it is a 3x1 vector, right? And here is the initial admissible control. Okay, this is my initial admissible control. Here is my initial state vector. It's a deterministic. Remember, initial state vector has to be deterministic. Initial admissible control. So remember, we talked about the difference between stabilizing control and admissible control. So, and there's always a debate. How do you pick that value when you don't know the dynamics? So this is always a challenge. And we try to relax it. We did that, but really mathematically it becomes really bloody in the proofs and all. And it does work, but it becomes really complicated. Okay? So now what we are trying to do is we want to see if the controller works. So you can see here from this plot, all the regulation errors, they converge without 8 seconds. So here are the learning rates. Okay, so with this, it converges pretty nicely. The control input also converges very quickly. So that means that even though the dynamics is unknown to the controller, the neural network is able to learn pretty quickly, even in the stochastic domain, and is able to do a good job, right? Even though the delays and packet losses are random. You see that? So that seems to work pretty nice. So now, I'm trying to use a feedback linearizing controller. So the feedback linearizing controller, basically, I'm assuming that in this case, that the dynamics are known at one instant of time. I'm designing a feedback linearizing controller. But remember that delays and packet losses are changing. Because it changes, a feedback linearization controller cannot keep the system stable.
F and G is now known.
F and G is known, but it's changing because of the delay and packet losses. So if you take the average value and you assume you know that, and you design a feedback linearizing controller, it blows up. Because the values are changing.
So it is not cancel the nonlinear.
Exactly, it's not able to cancel precisely nonlinear dynamics. Got it? Okay. And with our controller, just like we talked about it, you see the critique weights are bounded, the actor weights are bounded, and then we show that the identification errors, remember I keep saying that, we have to show that. So we show that the identification errors also converge, and so you can see that by about 8 seconds it's converging. Because it converges, you can see that nicely these things will converge at about 8 seconds. So the identification error is the most important part. Okay? So they all converge very quickly as the consequence converges, and you can see that the HAB error and the terminal constraint error also converges. Nice. Now let's say that for the sake of argument I want to compare. So there are 3 different methods here. One is the proposed NDP based optimal control, which is blue in the middle. The red is ideal traditional offline optimal control, which is the red, which is the bottom. And then the green is feedback linearization control. Look at the cost. So the optimal control that we developed is in the middle. So what is the offline based optimal control? So what is the offline based optimal control? Why is it showing a lower cost than one that I explained to you? What is the difference? So in the offline based optimal control, remember I told you the value polish iteration method, where you're holding the time and you're doing the iterations. So the good thing with that is the V hat will become V star at every sampling instant. So the method that you guys are doing or learning from me, basically we only do once a sampling instant, we are not doing the iterations. So V hat is not V star at each and a sampling interval. So there is an error in the, and that's why this controller is a little bit more expensive than if you're running it offline by using policy and value iteration. You see what I'm saying? So why? Because when you do that, usually if you look at our old notes, you flip it, we usually hold that state and then we do many iterations so that you make sure that it converges before you move to the next step. That's what we are not doing here. Because why are we not doing? Because time. There's only so much of time for the sampling interval. You can do that many iterations within the sampling interval. So in about 2015, we came up with a method called hybrid, where we combined that iterations and also the time, and we shown that it's much better. But then the issue there was how to prove stability. So the good thing is we are able to show stability. So I can pick based on the sampling interval. I can, and the processor that I'm using, I can pick a few iterations to be executed within the sampling interval. Whereas the other methods, if you stop that iteration, it will blow up. You see? So that's what we did. We call that approach called hybrid. Hybrid is a combination between the iterative fixed finite number of iterations and the time used. Okay? And it works pretty nicely. So if you have a faster processor, you could actually add more number of iterations within the sampling interval. That means you're making that V hat approach V star at every instant of time. You see? Got it? So any questions here? So that's what the 3 different methods we contrasted, and you can clearly see that a feedback linearization method doesn't work, and so forth, okay? And it's more expensive. All right? Okay, so I'm going to stop here. I think there may be coffee, right? I think this is a good time. All right, guys. So I'm going to stop, and when we come back, I know we are going ahead, so that you guys can spend more time in the lab, and you can ask me questions.